your slides, so please go ahead.
Okay, thanks. So I'm going to talk about TensorFlow-based maximum likelihood fits for high-precision standard model measurements at CMS. I apologize in advance if the format and focus is slightly different than the other talks. You'll see as I go through that the sort of order in which things have developed is a bit different than some of the other cases, since this is really something designed to solve a rather specific problem. So, okay. The background here on the physics side is, of course, precision measurements of the electroweak parameters provide stringent tests and an opportunity to over-constrain the standard model. And you can see here the standard G-fitter plot of NW versus weak mixing angle. So in this talk, I'm going to sort of, as briefly as possible, introduce a recent extensive CMS measurement on W production and decay properties, helicity and rapidity, which is available in this preliminary result here, and then mainly go into a deep dive on the technical and statistical aspects of the binned maximum likelihood fit, which is used to extract the results, and some corresponding implementation details. And I think that some of that is quite interesting, even if it's not really a general tool or framework. So part of the background here is that the PDF uncertainties are one of the major uncertainties for W mass measurements at the LHC, and you can see the example of the uncertainty breakdown here in the Atlas case. But there are well-defined correlations between phase-space regions, and you can use this to constrain the PDF uncertainties in situ. And there's actually a history of this already at the LHC in the weak mixing angle measurements from both Atlas and CMS, where in situ constraints exploiting the full details of the kinematics give a reduction in PDF uncertainties of about a factor of 2, which is quite important. The production of a W at the LHC is quite interesting. At tree level, you can think of it as all being QQ bar induced. And in that case, the direction of the W relative to the incoming quark determines the helicity because of the pure left-handed coupling. And so in a sense, the full information on the valence quark PDFs to some approximation in the relevant X range is contained in the rapidity differential cross-section broken down into the left and right helicity states. Now, in terms of what this actually looks like, in terms of the charge lepton kinematics, again, because of the pure left-handed coupling, the different helicity states preferentially emit the lepton either towards or away from the direction of the W. And so you have these characteristic distributions in the two-dimensional plane of the charged lepton, PT, and pseudo-rapidity. And you have these non-trivial templates for different states. Now, sorry, I'll go through this quickly, but it is relevant to the problem. So if you try and split this up by polarization states and by rapidity bins, you end up with these really non-trivial templates that are overlapping, and many of them. So you can probably see where this is going. So what we try and do is we try and measure these cross-sections from the 2D distribution of the charged lepton, PT, and eta in bins of rapidity and split into the 3 polarization states. So it's a bin template fit in a sense, but with many templates and many non-trivial aspects. And I'll come back to this later, but we also measure directly the double differential cross-sections, d sigma by dpt, d eta, in terms of the charged lepton kinematics, which is a slightly different problem technically and statistically. Of course, we have a full suite of theoretical and experimental uncertainties, which enter as shape uncertainties, and that's also important. So of course, we have the construction of the signal templates for background predictions, and then we have uncertainties associated with all of these things. So the uncertainties, just to break them down, there's a very detailed breakdown of systematic uncertainties, which include the QCD scale variations, the PDF variations, the background estimates, and the lepton energy and momentum scale. But some of these ingredients are really represented by literally hundreds of nuisance parameters, because the analysis is done very fine-grained in eta, and we also need to keep track of suitable variations of the PT dependencies in order to get everything right. So we have like hundreds of nuisance parameters for the per flavor for the lepton efficiencies, hundreds of nuisance parameters per flavor for the energy scale and momentum uncertainties in order to fully map, let's say, the correlations across the phase space. And so to give an idea, unrolled in 1D, this is what things look like. So this is a post-fit plot unrolled at detector level. So each of the blocks here is one bin of PT. And then within each bin of PT, you can see the pseudo-rapidity distribution the charged lepton. So you can, if you look carefully, you can see the Jacobian peak of the W. The bottom plot is for electrons, so the acceptance and efficiency is quite different in the forward region. So you know, there's quite a lot of information that goes in here, and you can see if you look carefully, you have the templates individually for the different W polarization states, and then smaller templates corresponding to each of the backgrounds. Z production with one lost lepton, the QCD fakes, etc., and all of those with uncertainties. So this is of course not very easy to read, but in terms of its representation as a maximum likelihood fit, which is of course the main thing that I want to talk about, any template shape fit can be expressed as a many channel counting experiment. It's sort of trivial, right? And then you can write the negative log likelihood as below, where this is essentially just the bind Poisson log likelihood plus the constraint terms for the systematic uncertainties, for the nuisance parameters. So what we want to do is we want to extract the cross sections from a fully profiled bind maximum likelihood fit, and to give some numbers that are associated with this result. So for the basic helicity fit, basic quote unquote, there are 40 measured cross sections or parameters of interest, let's say, in statistics terminology. There are 78 total processes, so different physics processes, including the fact that the W signal is split up into rapidity bins and polarization states. There are 3,320 bins at detector level, so this sum over bins is over 3,320 bins, and there are 1,354 systematic uncertainties represented as nuisance parameters, so these thetas here. So there clearly are some challenges to this. So we have tens of thousands of individual histograms which enter the fit, considering that each systematic uncertainty is represented as a shape variation via an alternate histogram. The gradients and the minimization need to be known accurately, and the good convergence behavior of the fit must be maintained, or else we'll never really be able to run this. And for the same reason, the time and memory consumption of the minimization needs to be kept under control. And at the end, the uncertainties and the full covariance matrix needs to be accurately computed in order to provide the needed information in HEP data, et cetera, to allow this to be used, for example, later on in PDF fits or the like. So what we do is we do this in TensorFlow, and the killer advantage here is really the computation of the gradients by backpropagation compared to what is typically done in more conventional tools. So the way that we would normally do an analysis like this with a bin maximum likelihood fit in CMS and probably up until now mostly in all the experiments is with something, let's say, RuFit plus Minuit based, where the gradients are always computed by finite differences, which has its challenges both in terms of efficiency and numerical stability. Now, the likelihood construction in TensorFlow is actually rather interesting. So you can write this sort of explicitly, and it was sort of suggested how I wrote this out with the indices. You have this N, which is the expected yield per bin per process. So it's a two-tensor matrix. You have this mu, which is the signal strength multiplier per process, so it's a vector. You have the thetas, which are the nuisance parameters associated with each systematic uncertainty, so again, a vector. And then, rather interestingly, you have this kappa, which is the size of the systematic effect per bin, per process, per nuisance parameter. So it's a three-tensor. If you look carefully, the way that this is written out is such that the nuisance parameter is constrained with a Gaussian prior, and then the yields are multiplied by kappa to the theta. So if you keep track of what that means, what it means is that the systematic uncertainties are represented by log normal variations of the yield of a given process in a given detector level bin, but with the correlation structure carefully kept track of through the fact that this kappa represents the size of the effect, keeping track of the effect per bin, per process, per nuisance parameter. And so that is quite important. And clearly that kappa three-tensor can get quite big, which is one of the challenges. So the way that this goes, as I said, is that we have this 2D tensor for the expected yields per bin per process, and this 3D tensor for kappa. We actually store it as log kappa for computational convenience, which parameterize the size of the systematic effects. there's some detail here, which is that in fact it's implemented with an extra copy to allow for asymmetric uncertainties, but that's a detail. The parameters of interest and the nuisance parameters are implemented as TensorFlow variables, and the full likelihood is constructed as a TensorFlow graph where the observed data counts are an input, which is good for like running toys and stuff. And some of the general strategy here is to pre-compute as much as possible with NumPy arrays, which are loaded into the graph via the TensorFlow data API from H5 arrays on disk. And I'll explain a bit more how that works. Double precision everywhere, offsetting of the likelihood to minimize precision loss, and there's a few other details. So an advantage of representing things in this way is that the above can be computed extremely efficiently in TensorFlow with just 2 tensor contractions, plus a small number of element-wise operations. And the reason is essentially that the number of expected events in a bin is the sum over the expected events from each process times the multiplier for the yield of that process. And that can be represented as a matrix multiplication. Likewise, the expected number of events from each process in each bin can be represented by this multiplication of the effect from the effect of each systematic uncertainty. But in the log space, this multiplication is a sum. And so it's essentially another tensor contraction of log kappa with the expected yields. And so the whole thing can be represented by essentially 2 matrix multiplications, plus, as I said, a modest amount of additional things, some complications for the asymmetric uncertainties. So in terms of what this looks like for the dense model, that part of it, the core of the likelihood calculation, the most computationally expensive part, which is the calculation of the number of expected events in each bin, summed over processes and including the shape morphing effects of every single nuisance parameter, is just this. It's these 2 matrix multiply operations with an exponentiation in between to convert the systematic uncertainty effects from the log space into the linear space. So it's a matrix multiplication, an exponentiation, and another matrix multiplication. And in the comments of the code, it's sort of written out more explicitly in a way which matches a bit closer to the way the formulas are written out. But you can imagine that this is an extremely efficient way to do this. And of course, the reshape and squeeze operations are zero ops computation. The rest of the likelihood construction is kind of trivial. It's just the sum over n log n plus n and the constraint term. So this is really easy once you get to the end. There's of course some details about protecting against 0 observed bins and things like that. So talking a bit about the minimization, here you have to do some non-standard stuff because these kinds of likelihoods, especially with asymmetric uncertainties, are not convex everywhere in the parameter space. So you want to use sort of, let's say, SR1 trust region type minimizers. We started with the trust region constraint minimizer with SR1 updates in SciPy, but then we sort of moved on and implemented our own native TensorFlow implementation of a sort of nice SR1 trust region minimizer, which has this interesting feature of eigendecomposition updates, which I'll explain why we did it that way. So here, the way it works is that contrary to a usual sort of SR1 type minimizer, instead of updating so the way these minimizers work is that you have an approximation of the Hessian matrix, which you keep updating during the minimization. It's the same thing here, but what we do is we keep, instead of the Hessian, we keep the eigendecomposition of the Hessian, and we update that directly. So the update of that is quite complicated, but then the rest of the minimization is super efficient. This is probably not the most efficient algorithm in terms of total flops, but it vector parallelizes extremely well. A lot of the other algorithms for doing this sort of thing have sort of nasty sequential steps that need to be followed, which are not super optimal. So okay, some performance tests. So this is an intermediate version of the analysis, but the numbers are sort of order of magnitude similar. So what I compare here is I compare Combine, which is sort of the traditional RuFit based framework, and then various flavors of TensorFlow. It's one CPU thread, many CPU threads, and then GPUs. And what you should pay attention to here is the likelihood plus gradient column, because this is the thing that needs to be computed at every single iteration when you're running a fit, right? So you can see this takes 830 milliseconds in RuFit, which is just single-threaded by construction. Now, what's interesting is that actually the likelihood computation itself is actually slower in TensorFlow than the RuFit implementation for reasons which we still need to look into in more detail. There's some numerical precision approximations and such there. But as soon as you have to compute the...
Yeah. Just to say, I see you have a lot of slides still. You have about 10 minutes, okay? Just to give it 1 or 2 minutes.
Yeah, no problem. I'll skip through things fast as needed. Anyway, so despite that, as soon as you go to compute the gradient, even on one CPU core, it's already much faster because you're doing it vectorized and it's not you're not doing a loop over finite differences. And then once you add more cores or GPUs, then it gets much faster. So the best case speed up here is already a factor of 100, which is pretty good. Now, on the other hand, if you go and do this with the actual minimization, then you have quite some overhead because the SciPy minimizers do a lot of operations in NumPy, which then runs on the CPU. And this was sort of the motivation to implement these native TF minimizers. Then you can see the amount of overhead is being reduced, let's say. But it's still not perfect, and there's still work going on. There's some interesting details here about the use of parallel 4 to compute the Hessian, which can speed things up a lot. The other thing I wanted to mention is that we also have a sparse tensor representation. And the reason why is that for the lepton differential cross-sections, we actually have 650 measured cross-sections rather than 40. And so this product of the number of processes times the number of bins times the number of systematics becomes huge. It becomes prohibitive to even keep these things in memory for the systematic uncertainties. But the templates are sparse because the response matrix is kind of diagonal. So each of these processes occupies like a small corner of the histogram. So we have a full sparse tensor implementation, which looks the same using sparse tensor operations. So again, 2 matrix multiplications and an exponentiation, where these are sparse tensors then. Some details here about saving memory with smaller indices. And here you can see that for this huge model, then the difference going from dense to sparse is like an order of magnitude in terms of CPU time to compute the likelihood and gradient. And you get rid of this like extra 8 gigs of memory usage because the arrays are not so big. There's some other details here about optimizing memory consumption. And in particular, these models have interesting features of large constants, which are several gigs in size. So what we do is we pre-compute them and store them in HDF5 arrays with chunked storage and compression, flattened, and then we read them back during the graph construction using the TF data API with quite some care to avoid having 2 copies in memory. So again, you can see the implementation here. It's sort of straightforward, but it uses interesting bits of the TF data API to read this back and critically avoid an extra copy in memory. I have the GitHub links for all of these things go to the specific code blocks, of course. So, okay, the code lives here, not very streamlined since the priority has been on a particular set of physics analyses, which are in progress with it. And it's currently somewhat intertwined with the existing CMS fitting tools. But there are 2 scripts, one which essentially creates the inputs to the TensorFlow graph from text data cards and root histograms in the format that we use for the CMS fitting tools, and outputs them to HDF5 files containing these flattened arrays for large constant tensors. And then there's the combined TF, which constructs the graph, loads the constant arrays, and then runs fits, toys, likelihood scans, etc. There's an intention to push some of this stuff upstream, in particular from the minimization side. And then I think there's an opportunity to sort of take some of these optimizations from here and implement them in CFIT or PyHEP or some of the other more general frameworks. To first order, you run this in 2 steps, and there are some example cards in the Git area there. So, okay, I'll skip some of this, which has to do with sort of running one fit and then extracting a lot of different results from it, basically using Jacobians, which are constructed on the fly to sort of transform the measurements and covariance matrices. So this is also a sort of workflow efficiency thing. you can see that we do make use of these covariance matrices, which have non-trivial structure. So this is an example of a correlation matrix, but this is a small subset. This is a 20 by 20 subset of the full covariance matrix, which is 1394 by 1394. And the whole thing is computed at sort of full numerical precision without any finite difference or anything, from admittedly not the most efficient way because you have to loop over the rows. And then, okay, here are some of the results. I won't really go through them. You can read the paper. It's not really the subject of the talk, but there's a large set of them. There's also some interesting features related to computing the impacts of groups of systematic uncertainties on the measurement, which is also done by manipulating the Hessian matrix that you get out, again, to avoid doing any finite difference or toys or anything like that, which would be computationally prohibitive for the main block of results. I think probably the last thing I want to say then, so that we leave some time for questions, is that, okay, so these measurements, which I'm talking about, and again, if you're interested in the physics of this, I do encourage you to go read this paper. It provides polarized differential cross-section measurements of W production with significant potential for PDF constraints, and it's an important precursor for future NW measurements. And that's sort of the motivation for why we developed it in this way, to give flexibility for this. The analysis is designed to allow in situ constraints of the PDFs with maximum statistical power, considering the experimental and other theoretical uncertainties. And the statistical interpretation required the development of new tools and algorithms based on TensorFlow. They're also used by some other CMS analyses up till now. But the main focus was on solving this very specific problem of very large bin maximum likelihood fits with a lot of different statistical interpretations needed. And clearly for this, there are substantial gains in speed and numerical stability with respect to the traditional tools. And the main point, as I said, is that this enables more sophisticated and accurate modeling of the systematic uncertainties, which are crucial for future measurements. So we can basically avoid now the situation where we say, okay, we would like to model a given uncertainty with 50 additional nuisance parameters to map the correlations, but we can't because it will break the fit. This is not going to be the case as a result of having things implemented in this way. So, okay, I think this was sort of an overview. Clearly, there are many details, and I'm happy to sort of go back to a particular slide as part of answering the questions that people have.
Okay, Josh, yeah, thanks very much. Particularly like the fact that you also mentioned, I think, in one slide that you were contributing to codes upstream, which is something we don't do too much in HEP, but we should do more, especially when we're using data science tools. That's very nice to see. I can share. Oh, okay. You're already having the picture. Oh, it's very small. Otherwise, I can share it for you.
I can make it bigger. Yeah.
Yeah.
Okay. So maybe I'll go from the bottom. So the light blue bands in the ratio plots on slide 15. Sorry. Yeah, so the reason why is actually a little bit interesting and silly. So the fit includes bin by bin statistical uncertainties on the Monte Carlo, which are actually quite large. And so what ends up happening is that the central values in the post-fit get profiled out. And this suppresses the fluctuations in such a plot. It's because we have less Monte Carlo than data in terms of statistical power.
If you go to slide 17, there's another question.
Yeah. Yeah, so the total number of histograms is huge, but we really do scan through them by eye in the sense that what we do is we look at ratios. So what you have to remember is that the actual number of histograms in terms of central values is basically 78, right? And we look at them in this unrolled form, which is okay, it's a bit challenging. We also look at them in 2D. But then for the systematic variations, we look at things in terms of ratios to nominal. There, you can make heat maps in 2D and we make big HTML pages with the plots arranged in dense grids, and we look through them. We also have some scripts which look for sort of anomalously high ratios, and we did clip them manually in some cases where there was weird things going on in terms of statistical fluctuations in the denominator or whatnot.
Right. And the last question is whether there are plans to migrate to TensorFlow 2.
Yeah, so I think one of the, so let's say, aside the fact that this code is not super modular or very nice because it was developed in the course of an analysis, one of the other issues is that the computation of the Hessian is not very efficient because it relies on an explicit loop over the rows. So I think we would like to do something which is more efficient at handling higher order derivatives. Aside from TensorFlow 2, which is a possibility, and we have to see how much this parallel 4 functionality has evolved, we may also look into JAX, because JAX has some quite good semantics in terms of this VMAP for vector parallelizing over autograd. And this could be another path to implementing the Hessians in particular more efficiently. This is by far the bottleneck for runtime at the moment. If I run this fit now, it'll take 3 minutes to run the fit and then half an hour to compute the Hessian at the end. So.
Okay, seems we're done. If there's nothing else, thanks very much.